So, this talk was about hardware and software co-design with FPGAs, and I will explain what that means a little bit later on. So, the very first thing that I wanted to do, though, is give you an example of a real-world system. A real-world system could be something like a smartphone. So I want to preface this with a couple of questions that I wanted to ask you guys. And I want you to respond. I want you to tell me how you would build a smartphone nowadays, what components you would use, how do you choose them, what vendors do you use, how would you communicate between components, and how would you test your system? Do you have any idea of how you do some of these things?
I think by industry standards, it for sure has to be waterproof now.
Sure. Waterproof.
I'm thinking mechanical, right?
Sure. I want to make this as practical as possible, and I want to show you that what I'm about to show you today has place in real-world systems. So, some things that come to mind is you need to worry about power constraints. You need to worry about heat for mechanical, for sure. On the next slide, I put a couple of things that you might want to worry about. Does this seem reasonable to everybody? You need internal memory, external memory, a processor to do some sort of computation. There's a touchscreen display, right? So you need some sort of screen digitizer to digitize what you touch on the touchscreen into the digital world so that it can understand. You might not think of it, but there's also an RF interface to be able to talk to cell phone towers and everything like that. Once you get signals from RF, you need to do digital signal processing on it to make sense of those RF waves. There's USB. There's a lot that goes into a smartphone. And if you were to try to compartmentalize all of these things into ICs, that's how it used to be. We used to have a lot of ICs for specific things for a phone. And this applies to a lot of other systems too. Everything that I sort of mentioned on the previous slide is here, and this is how it's connected to in this make-believe cell phone that we're talking about here.
What would be different about an IC? Is it still designed like this, but they're like each individual components? Or?
So you'd have an IC for a particular component, like you'd buy from a vendor. These are all different vendors that you see, and when you're designing something like a cell phone, you say, like, okay, I need something to do DSP or baseband processing, and you find a vendor that you think is good to do that, and then you put that chip in your design, but then you need to do an overall power analysis and calculations, and if this is going to be the right fit for your overall design. And when you have all these ICs, that kind of makes the routing of the PCB a little bit more complex, as opposed to what I'm about to describe. It takes up a lot of space. Like, this used to be an older cell phone right here. You remember those like bricks? It's because the ICs took up that much space, and they were able to bring down the size of a lot of these components and even integrate them into a single chip. A lot of times with different components that are really high speed, you need to have the same copper lengths on the PCB so that they reach at the end destination at the same time. So what a lot of people who do board layout, what they'll do is they'll actually make squiggly lines with the copper traces so that they match the lengths to get to the IC the same time other signals do.
It's like equal length headers for a car. Sorry.
So that's why I have like match all the lengths there. But this is an issue when you have a lot of ICs and you have a lot of high speed stuff. You have to match the lengths with a lot of these components.
Really?
Yeah.
That's why you see those little squiggly lines?
Yeah.
I always wondered about that. I was like, why is that really necessary?
Yeah. For some components, yeah. Yeah. So we're moving along in terms of technology progression. They've invented something called SoCs, which is system on chips. And system on chips are pretty cool. A lot of the components that you saw on the previous slide, they just jam into one silicon die. And they have all that functionality in one chip. Now, it can't like do everything. There's some constraints to that. but it was a lot better than what it used to be. Sticking with the cell phone example here, there's an SoC, Pinwell SoC processor on a smartphone. So they're using processors on phones, like complete SoCs with processors in the SoC. So there's like cache and memory, and there's DDR, and there's all this stuff that used to be separate components. It's all in one SoC.
So is that like what you'd be getting when you get like a computer with an integrated graphics card or something, rather than like a dedicated?
Well, an integrated graphics card, if there are some GPUs that exist on an SoC, so you can have a processor and a GPU on the same silicon die. For example, TK1 is one of the very famous ones that do that. They do TX2.
So that kind of process of putting them together is like the same, no matter what the component is. Like it could be a GPU or it could be like the memory module or something.
Say that again?
So that process is the same, like no matter what. Like if you're putting a GPU on there or you're putting any of these other portions like onto a single SoC, it's just the same. Like you're just integrating it all into one.
Yeah. To make an SoC, it's actually really expensive. But yeah, you take what you want in terms of components. I mean, I don't know all the details about it, but I know that there are some limitations. But for the most part, they can consolidate a lot of stuff into one package.
Does that mean one lane?
Silicon die is one silicon wafer chip.
Oh.
So they have just one chip, one package, having all these components in
There
there.
was like the ground plane and then something else, and that had everything in there.
Yeah. Actually, I think in the next couple slides, I think maybe the one after this one, I have what SoCs look like inside. I'll show it to you in a second. But after, SoCs are awesome, but one of the limitations with SoCs, or at least one of the limitations used to be, is the hardware didn't change inside. Like, whatever you put in an SoC, it's static. Like, you spend a bunch of money to make this thing as small as possible, and you can't change anything about it until they started adding FPGAs to SoCs. And with FPGAs, it stands for Field Programmable Gate Array. I'll show that on the next slide. It actually allows you to dynamically change the hardware inside the SoC, which is really awesome. So now you don't have like a static design. You can have some flexibility in with your SoC. And you have, again, like a whole sandbox of all these toys that are in an SoC, like a processor, you have some memory.
So it makes like the on-chip components be modular?
Yeah, for sure. And you can interface with the outside world any way you want with an FPGA. You don't have to be like, well, these are only these pins, and I'm only routing these out to this out of this SoC. Now you can say, well, I have an FPGA, and the person who's designing this can decide what they want to route out. Some of the go ahead.
What's the functionality exposed? Is it just like pins, like header pins, so you can then?
Yeah, a lot of the times they'll have BGAs, which is ball grid arrays, and some just have an insane amount of pins. But yeah, it's essentially just pins being routed out on the PCB. Some of the pros to having something like this is it's smaller, reduced power, reduced size, more efficient. It's extremely flexible. But what a lot of not complaints, but a lot of the times having something this complex, it's a steeper learning curve for a lot of people. And also having an SoC, it's different than just having a pure standalone FPGA. So an FPGA is awesome in and of itself, but it's really neat having it inside of an SoC. But if you just have it inside of an SoC, you don't have as much FPGA space, and they call that fabric. So whenever I say like FPGA fabric, that means the amount of gates and just space that you have to manipulate hardware. So there's not as much FPGA fabric if you pack it into an SoC. You can imagine, because there's a lot of other stuff involved. So I'm not saying like SoCs and FPGAs like are your one-stop shop for everything that you'll ever do. You have to weigh them, pros and cons of everything. This is a little bit more on what an FPGA is. It stands for Field Programmable Gate Array. The reason why it stands for that is because it's field programmable. After you've already manufactured it, you can go out in the field and reprogram it. And it's all about modifying circuits. You're literally changing hardware. It's really neat. It's not like programming in the sense where you have some CPU going through some instruction set. You're actually modifying hardware. Yeah.
So, is this mostly used for prototyping, or is there also like packages meant to like go out into products?
Both. So you can use FPGAs for prototyping. For phones, I know that they use something called ASICs. And for ASIC designs, it stands for Application Specific IC. And a lot of times, the type of design process that you go through is very similar to how you'd go through with FPGAs. The thing with FPGAs is you sort of, the way how it's, the internals is like you have everything connected to everything else, and that's how you're able to make a circuit any way you want. With ASICs, you have just very specific wires going to specific things. That's why it's called application specific IC. And it's incredibly efficient, but not very flexible, because once you make it, it's done. That's like the only thing that it's doing. How you program something like this, I say programming lightly, and that's why I put quotes around programming, because in this field, it's weird.
G-code, right?
Kind of, I guess. It's very strange, because like a lot of times at work, at my work, there's some confusion, like, oh, like you program, so you do VHDL. Oh, well, VHDL's not really. It's kind of for electrical engineers, but it's this weird domain where it is programming, but it's programming circuits.
Changing gates and registers?
Yeah, you're manipulating. Yeah, you manipulate gates to make a circuit.
And you're assigning different roles to different pins, right? Physical pins.
Yeah. And this language, this programming language, is most commonly done in VHDL or Verilog. And what makes it even more confusing is that the lines between software and hardware can be even more blurred than what it already is, because you can do stuff like instantiating soft cores in the FPGA fabric. And by that, I basically mean you can make a microcontroller, like a microprocessor, microcontroller, in the fabric, in FPGAs, because all a microcontroller is just a bunch of circuits and gates and registers. And you can make a microcontroller in the hardware. So like Arduino or something like that, or Atmega, or that sort of architecture, that design, you can place that in the FPGA fabric and have a microcontroller in the fabric. And you can still, if you have enough space left on the FPGA, you can still use the remaining space for other dynamic circuits that you want to make.
So, are you like in text editor or something writing code, like I would picture a program, but it is making changes at the hardware level, or you're like actually like swapping parts out of the board or something?
You are in an editor. They have something called Vivado. That's for Xilinx tools. For Microsemi, it's called Libero. Every sort of vendor has their own thing that they do, and they have like a huge tool chain of stuff, and it helps you develop for their board. It's kind of interesting, this space, though, because if you really learn Xilinx tools and Vivado, you're almost kind of stuck in this world, and you can only use their tool chain for their boards.
Yeah.
But if you use Xilinx tools, you can use Xilinx for their boards.
An open standard across that.
I haven't seen one.
So even like the basic instruction set might be different across the different competitors?
Yeah.
Is it like C++ and then you go to this other place and they have like extensions?
Well, here's the thing. Like, VHDL is VHDL, so you can go across platforms to different vendors like that. But in terms of the tool chains and how they synthesize the circuits and stuff like that, it's a little different between all of them. So if you have one bit stream, bit stream just means like the end artifact of what you've created. After you program VHDL, it goes into a bit stream, and then you put the bit stream on the FPGA, and that allows you to exploit whatever circuit that you just made on the FPGA. But yeah, It's interesting because instantiating a soft core in the fabric, you can also write C code on that microcontroller, which is weird. So you're writing C code on a microcontroller that you created in FPGA fabric. And you can create more than one microcontroller. You can create several. Very commonly, they create ARM microcontrollers in soft cores. Some SoCs have hard cores, like an ARM hardcore in the same package with an FPGA, so you don't always have to instantiate your own software. Because if you instantiate it, or if you create it in your fabric, you take up gates and space, so you're eliminating space away from your design.
So assuming you have the fabric available to you, could you instantiate several soft cores and then create something that runs C++, something that runs Python, something that runs something else?
Yes, you can. You can, as long as a microcontroller, you can't generally just instantiate just any microcontroller and run Linux on it. You'd have to have something that's beefy enough to run Linux. So a lot of the times you'll have like a ARM, you'll instantiate an ARM or something like that, or you'll have even an ARM hardcore, and you'll have that run Linux. But generally you won't run Linux from a soft core that you create in Fabric. I don't usually see that. That takes up a lot of real estate on the board. If you're going to go that route, you might as well just pick an SoC package that has a hard core already dedicated, because that's going to be faster than just trying to instantiate it in the software or in the FPGA fabric anyways. So if you have hard core, like an ARM Cortex A whatever processor, and you can run Linux on that, and then you can have Linux interface with the whatever design that you do in the hardware.
So could you get like truly parallel processing? If you have two hard cores just running at the same time?
Yeah, you could, for sure. If you can though, you would want to push your design into an FPGA, like in terms of gates, as opposed to putting on the soft core, because I mean, the whole point of the soft core, it does make it easier for you. It is a little bit more flexible, but the commands are being executed sequentially. If you put your design on the actual fabric without having to go and resort to a soft core on the fabric or something like that, then you can get truly parallel performance.
So if it's better to have a hard core, since it's going to take so much real estate, when would you want to instantiate a soft core?
So you'd want to instantiate a soft core when you want to do something very basic in the FPGA, like configure registers. Something that maybe, let's say that your hardcore, let's say that you have an SoC with a hardcore. Not all SoCs that have FPGAs on them have hardcores, like an ARM hardcore. But let's say that this one does, and you have an ARM hardcore that's doing some advanced image processing process, or you're creating a web server on this ARM controller, this ARM microcontroller, and you might want to have a microblaze to configure the registers at boot up or something like that. I mean, you can have the ARM hardcore do it, but it might be busy doing other things. It really depends on use case.
Or you could like, kind of like a server, spin it up and down. Like you could instantiate it, and then when you're done with it, you don't need to keep it around. Right? It's like any other form of memory or anything, not really.
There was mention about in-programmable applications, or I think that's what it's called. They touch on it a little bit. I have some videos that I want to show you guys, but I think it's possible to, as you're running your application, to dynamically change the gates and hardware in lifetime. Generally, you'll make a bit stream, and then you'll put the hardware on the FPGA, and then that's your application. You can change it later in the field if you want to, but I haven't really seen like, oh, dynamically changing the hardware as your application is running. But I think there are some applications for that, and vendors for some boards do allow that. Again, it just comes down to like what SoC you pick and what you need for your applications.
That'd be interesting though, because if the fabric space is like the limitation, then that kind of like, if you need something at a certain time, it doesn't have like user forever.
Yeah.
I actually have a pretty cool example with this. It's not exactly a software, but we were working with this development board with an FPGA on it, and didn't have a way to communicate over I2C. So we just wrote in the protocol to read in, didn't talk to an Arduino, so we can see what was happening inside the FPGA. So that was pretty cool, because if we couldn't find something to just like hook onto an I2C line. So just kind of designated a couple of pins on there to talk.
Are there templates for like making cores?
Yes. Uh, it's probably not as hard as what you guys are thinking. A lot of the times you'll have a Vivado editor that you can click and drag blocks onto a design. And
Blocks are a function already.
yeah. So going back a couple slides, you see all of those. All of those would be an IP core that you'd put into your fabric. You can just click and drag. If you need anything that's a little bit more advanced, you may need to write your own VHDL. There are some designs that you can totally exploit an FPGA in an SoC without having ever written VHDL.
That's interesting because I'd written an article, I'd read an article a couple months ago about the prototypes for the PlayStation 5 and how basically it was like a massive FPGA, and it makes sense now because it's like at that initial prototype stage you want as much flexibility.
Right.
Yeah, that's what I was wondering is why, like, because kind of Jared's question and yours mixed together. It's like, where's the line at which FPGA becomes usable? Because, like, how often are you going to change something out in the field versus, I would think once you get to your final design for, like, most use cases, like, this is good for, like, as long as you really need it.
Right, and then at that point, the company might consider going into ASIC, looking into ASIC territory. And
So
that will
ASIC
just,
can be
I mean, FPGAs are efficient, but ASICs are incredibly efficient and consume very little.
That process of using an FPGA to like iterate on whatever your ASIC design would be.
Absolutely. That's actually very commonly that's how my work does it, is we have FPGAs and then we just iterate on a design over and over until we get it right.
Is the end goal to get to like an ASIC infrastructure, but you use the FPGA to kind of shape and mold the ultimate form?
Well, a lot of the times people will use FPGAs as the end product anyways, because it's efficient enough. But to go to an ASIC, that means the only way that makes sense is if you're selling to hundreds of thousands of people. Because to make an ASIC, it's actually very, very expensive.
Like right now, I know like whatever things mining Bitcoin and stuff, they're all like getting into like making their own specific chips, and they have these companies competing. So that's a point at which like whatever the smallest level of like efficiency matters. So it makes sense that they would go with that kind of design.
Right. And I mean, they're selling to a lot of people who are interested in this. So I think right there, it's this little block for this microsemi core is called in-application programming, and this component allows you to, I guess, flash the FPGA fabric while your application is running. So there's some SoCs that have this. You can see that there's a this is one SoC. This is a microsemi part. In the SoC, there's an ARM Cortex M3 processor. The M3 processors can't run Linux, I think, because they don't have an MMU, but the ARM Cortex A processors can. So memory management unit. So if there's anything that you don't know, please let me know. But so you'd run bare metal applications on this. So essentially, you'd run a C program, put it on the hardcore, and then you can have that interface with this fabric that's over here, and this is through here. Now, the really cool thing about microsemi technology is that they have static RAMs, which is on the bottom right here, which means when you flash your FPGA, it's stored in memory, which is interesting because I know there's a lot of Xilinx parts that don't do that. So if you flash an FPGA, it will go away during the next reboot cycle. But how you prevent against that, or what I've done, and I'll show you this a little bit later in the demo, is if you have like an ARM hardcore, you can actually have the ARM hardcore during the bootloading process load in the FPGA fabric, or load in the bit stream into the FPGA. So it seems like it's persistent, but it's really not.
It's like it's serving as a cache almost or something.
Yeah, like a memory. Yeah, I mean, the bit stream really is stored in non-volatile memory somewhere, but it's stored and packed in with the Linux operating system. So when you're booting this processor, the hardcore, the first stage bootloader is like, oh hey, I also have a bit stream. Let me program the FPGA while I'm trying to get the rest of the system boot up. It's just another thing that it has to do in its initialization process.
Well, the only way you can get around it then is either if you have static RAM or you have a hardcore. But if you don't have either of those, it's just going to go away every boot cycle.
Or you need some non-volatile storage on the board that actually does that transaction for you. if you don't have a FPGA with this sort of technology in it. But yeah, there are some FPGAs that have static RAMs in there, so when you load the FPGA, it just stays on there. So it depends. This space is very flexible. So it's basically, what do you want for your design? You could probably find something like that. Yeah. So these are what the inside of some of these chips look like. This is a microprocessor. This is an FPGA. Here you can see that there's just a bunch of gates. An SoC is just sort of a accumulation of all these things. This is a digital signal processor. And this is a microcontroller.
You know, maybe in a later session, if we ever do revisit FPGAs, I'm gonna invite Stewart. I'm gonna invite Stewart, who's like an older engineer. He used to work with at Foresight Sports. He was the FPGA engineer. That's all he did.
Oh, really?
And on his monitor, I never really understood what was going on, but he had basically the FPGA in the middle. He had that displayed.
Oh, yeah,
massively.
yeah,
He
yeah.
was like manipulating each
Yeah.
little.
So the cool thing in Vivado is after you make your design, you can actually, there's this editor that they have where before you even flash it onto the FPGA, they show you what bits, like physically, they'll show you like a picture of this, and they'll show you what areas are actually being utilized, and they'll highlight different parts, saying, you're using this, and this is this percentage of the overall gates that you're using. It's pretty cool that they're able to do something like that. But so I haven't even mentioned what hardware-software co-design is yet. So here's a couple commonly accepted descriptions for hardware-software co-design. So some people say it's the partitioning and design of an application in terms of fixed and flexible components, or a design methodology supporting the concurrent development of hardware and software, co-specification, co-development, and co-verification in order to achieve shared functionality and performance goals for a combined system. Hardware-software co-design means meeting system-level objectives by exploiting the synergism of hardware and software through their concurrent design, or simply co-design is the concurrent development of hardware and software. So it's sort of this blend of, you know that you have some software components and you know you have some hardware components. Where do you put your design? You have this thing in your head that you want to do. How much of it should be in software? How much of it should be in hardware? You have the option to make soft cores. You can instantiate a microprocessor, microcontroller in the fabric. Do you decide to use that and just use a fully functional FPGA, like no SoC, or do you use an SoC with a hard core? Like, it really depends on what your requirements are.
What kind of build you're going for.
Right. And here are some of the trade-offs that you can expect. So this is hardware performance versus software performance. So on the right, this figure shows a cryptographic, several cryptographic implementations in both software and hardware that's been proposed over 2003 and 2008. On the right side here, this is hardware. You can see that this is better performance than the software variant. The bottom x-axis here is the bits per second. So you can see that you get more bits per second if you have hardware dedication than if you just sort of perform things sequentially in software. So I think it's also important to note, though, that even though the hardware executed more operations in parallel than software, the software actually may outperform the hardware, since a lot of higher-end microprocessors actually have higher clock speeds, like significantly higher clock speeds. Like, for example, my computer at home does 4 gigahertz, but you can expect a clock that's in fabric, like this Cybo board that I have that I brought, I can get like 200 megahertz, so it's not nearly as fast. However, you can do a lot more stuff in parallel. So that's why you might actually see processors outperform the hardware components. So in reality, the differences between performance of hardware and software is not that great of a metric for comparing things. It doesn't show where the hardware really shines. It shows that it happens in more bits per second or happens more in parallel, but it doesn't it doesn't show you the efficiency gains that you're actually getting. And then in the next slide here, there's actually energy efficiency comparison.
So gigabits over joules?
Yeah, yeah. Gigabits over joules. So how much power are you actually consuming? So this is sort of the metaphor that I like. Imagine that you're in this really nice Corvette and you're able to go incredibly fast. And then there's a bus. And your goal is to get from one point on the map to the other side of the country or something like that. Which one's going to get there faster? Well, the Corvette is, but you can get more work done with the bus transporting people. So, yeah, it depends on what your application is. If you need just an insane amount of performance and you can give up power for that, then you can go with the processor. You're going to have a processor that gets pretty hot, right? And yeah, that might not be okay for your application, especially for applications that require surviving on a battery. A lot of applications need to have very long battery life, so you want to utilize as much of the hardware as possible because it's a lot more efficient. Here you can see that you actually get far more gigabits per joule using CMOS, and this would be equivalent of like ASIC technology.
What is CMOS?
I actually don't know. Something metal oxide semiconductor. I don't know what it stands for exactly.
That's not what they use for cameras, right?
Yes. Yeah, I believe so.
Like super
Yeah, you'll
specialized,
see like a lot of CMOS cameras or something like that. Yeah, Sony CMOS or something. Yeah.
It's like that's the only thing they can do, but they do it like ridiculously
Yeah.
well.
Yeah, exactly. And these are all architectures of different hardware. So you can see that different architectures here, depending on what it is, you get a lot more with having a hardware dedicated application. So hardware sounds awesome, but again, there's pros and cons to it. You get to decide what you need for your application. And if you're choosing something that can do like a hardcore where you can do software on it and an FPGA that can do stuff in parallel, you need to decide on where you want your design mostly to go, not just to increase the efficiency of your design, but also for making things easier. Because if you move stuff to an FPGA, it's more complex. There's more things that you need to think about. To do simple things in C, you need a lot more lines of VHDL code to do, because you're designing circuits to be able to do it. But here's just a brief glimpse in some of the trade-offs. Here's efficiency versus flexibility in some of your designs, depending on what architecture and what programming platform that you're using. Primarily, a lot of the processors nowadays, like ARM and stuff like that, they'll use RISC architecture. I think so, yeah. And then as you go more to the right, you lose flexibility, but you gain efficiency. So you might be surprised to see FPGAs so far to the left. But it's somewhere in the middle, like it's flexible, but it's still efficient. But if you go more to the right, you're giving up flexibility. But the efficiency gains are insane. Any questions?
So far, I am getting a kick out of this stuff. Very much reminds me of Armored Core gameplay, where when you're making your build, it's like you want energy efficient, you want a better processor, you want a okay, this better processor is great, but it takes up a lot of your generator energy. It's heavier, but it does have a bigger scope, more range.
Yeah.
Sorry.
No. Like having your designs are not just limited to processors. I wanted to sort of expand the horizon to show you guys that there's other solutions out there for you guys. You don't have to choose a processor if you have some computation you need to do. If you have some application you want to do, think about it in parallel and how you can actually exploit having something that's hardware dedicated, because that's actually going to be more more efficient for you. And it depends what the application is. Like images and image processing is really good actually to do in hardware, because there's a lot of data, and you can, for a lot of image processing algorithms, you can do a lot of this stuff in parallel. So hardware is a really good choice for that. If you ever wondered what an inside of an SoC looks like, this is like a diagram of some of the components. This is the Zinc 7000. This is actually the family of what this Zybo board is. So this SoC is what you'd see when you're doing design for this board. They actually have this in the editor, and you can open it up, and you can click on different peripherals that you want in the hardcore, and you can select, oh, I want this one, I want this one, I want to route this out to the programmable logic. You can see in the bottom right-hand corner, there's PL for programmable logic. You also see the terminology PS, which is right above that. If you can see that, that's processing system. And so that's how I'll sort of refer to the software domain, where software lives, and then the hardware domain, PL versus PS. There's a couple of videos here. I don't know if audio will play. There's another video here. This is actually a different vendor. This is Microsemi, and they have the Smart Fusion. This is the SoC that I showed earlier. So this is their board that they have here. Video is a little bit longer, but I still think this is very interesting because they show driving, I think, brushless motors and stuff like that. So with the FPGA. So I wanted to sort of show the Zybo board. Zybo Z7-20. This is the board that I brought here today. Yeah, it's similar to the architecture that I showed before, the Zinc 7000 family. This is the application that I did at home. So this is what I'll be showing you guys. I have an HDMI output, like a camera, like from a GoPro or a laptop. And it's being streamed through the Zybo board, through HDMI in. It's going through something called Video Direct Memory Access, which is basically you have this memory in the programmable logic, and it's being piped up to the processor system through something called AXI interconnect. That's a lot of the times. There's other sort of protocols, but this is just a protocol for the processor side to talk to the programmable logic side. And I have the processor system running Linux, and I have a Python web server running on the processor side, processing side. And then I have another application that I run to run the it's basically like the programmable logic controller. So I basically get to decide when the PL starts by the processor side. So I built in some logic where things won't get going, things won't start until I tell it to start on the processor side, because I need things to be in sync and I need things to be ready. So you can do that. You can basically hold off and then enable stuff from the processor side and then have the hardware work accordingly. Because a lot of the times you need to worry about synchronization between the processor side and the programmable logic side. The Python web server is streaming whatever it got from the HDMI output to the network and streaming it to another desktop or computer. I could have pulled this up on my phone or anything like that. This is what the block diagram looks like. So this is in the Vivado editor. I just clicked and dragged blocks. Not that bad. However, those two blocks that are highlighted, I actually made subcategories for. This is what it really looks like. So these are the blocks that I dragged in here. I just categorized those this way because it's nicer to look at, but this is essentially what it is. So you have HDMI in over here coming in through the HDMI decode, and then you have the video stream going out into the VDMA and then going into the Zinc processor. What you see here is supporting components to allow me to facilitate that.
So it's everything around the FPGA.
It's exactly what you saw before. These blocks right here. This block is the VDMA. I just expanded it. And this block is the HDMI decode. I just expanded it.
So this is actually the editor?
This is actually the editor.
Oh,
This is what. Yeah, a little bit.
Just in that you can.
Yeah. The thing is like you can actually go in if you want to and actually change the VHDL with some of these things, or you can add your own cores to this if you want.
Which was this block? Like, which one's the high level?
This guy?
Yeah.
This is the VDMA. I actually go through and I highlight certain portions of data paths. So this is where the HDMI in is, This is where like camera or the laptop would be streamed through, and then it's going through here. This is basically the RGB stream, the RGB data. Goes through here, into the VDMA, goes into this AXI interconnect, and then connects to the Zynq processor. Now here, even though I have this in this editor, I'm not instantiating a processor. I'm not instantiating an ARM core. This is just represented by the interface into the processor system. So these are my interfaces. I can double click on the block and do more options and select more ports to the outside world, to the programmable logic. But everything outside of this Zynq block is programmable logic. The stuff that's inside of the Zynq block can be represented as the processor system. But I just need a way to represent having connections go from the processor system out to the outside world. So again, just to reiterate, I'm not instantiating a Zynq core here. I'm just using it as an interface, and everything else I'm instantiating in the fabric. Here is, so just like this one, how this was the image data flow, this guy over here is the programmable system control that controls the HDL. Remember how I said I have another script in the Linux system that actually controls the HDL? This is the flow of the control of how I'm controlling the programmable logic. So it goes out of here, goes over here to an AXI interconnect, and then there's two locations that I'm controlling. This is a master. I know this is kind of hard to see, but this is a master, 2 ports, so I'm controlling 2 blocks here. I'm controlling the VDMA itself, the Video Direct Memory Access Controller, and then I'm controlling LEDs on the outside just to do sanity checks, so that when I have my operating system up and running, I can write to these addresses in physical memory and see LEDs go on and off to make sure that I know my bit stream is loaded on to the FPGA and everything's working properly. You'll sometimes do like debug checks like that, just throwing stuff. Yeah. You have to get very creative to debug this. Whoops. So this right here is just my reset signals. The only reason why I highlighted this was to show you that even though this looks intimidating, a lot of these signals are just reset and clock. And all resets, depending on what you're doing, but a lot of the resets are tied together. So when you push a button to reset, you're resetting all the IP cores. And I'm just showing the lines going to all of them. You can see it stems from this Zynq processor, and it goes out into this main processor block that kind of stems out and reaches across all it does different sort of flavors of reset. Sometimes there needs to be active high, sometimes there is active low. In terms of like turning it low will reset it instead of turning it high. There's some IP blocks that need to be held high. If the voltage signal is low, then it's actually reset. And then there's some the opposite way. So this block over here just kind of helps me make sure the right signals, the right reset signals are being sent to the right IP cores. So everything highlighted again is just reset signals, and then everything highlighted on this one is all clock signals. And I mentioned memory before. So this is the physical memory that I need to write to on my Linux system to access these IP cores. This is the AXI GPIO, which contain the LED. This is the AXI VDMA control, and then this is just general memory that is being flowed into the processor system. The VDMA, this is where the RGB stream is being dumped to. Video Direct Memory Access. So it's basically the processor system accessing memory directly. Now, I don't want to get too much into this, but this is just here for completeness. And this is what I kind of did to get the processor system up and running. It's not like you're given a processor system and it has all the software for you. You need to build the software. So I built my own bootloader, U-boot. Bitstream obviously goes with that, Linux kernel and root file system. So all the components that you see in like Linux, you have to build yourself. But that gives you a lot of control over your system. There's like a lot of tutorials out there on how to do stuff like this. But for the sake of time, I'm just going to show you this very quick. This is the project at home that I did. Here I have the Zybo board. I'm going to plug in an HDMI cable. This HDMI cable is coming from this laptop here, as you can see in the back. I'm already connected to the board here, and I can run a command to start the DMA transfer. And I can open a window here, go to the IP address of the board. And here in a second, you'll see the screen of this laptop. Alternatively, you can also use a HDMI camera, like a GoPro. And before I show the web server here, you can see the actual input from the integrated logic analyzers that I have built into the programmable logic. Just to give me a little bit of understanding of what's going on. And going over here, opening the IP address again, or of the web server. And that's coming straight from the GoPro looking up. That's it. And that's all I had. There's a section of this where I was actually going to bring up the Vivado system and actually show you, actually like an actual project that I load on from scratch. But we can have a brief intermission if you guys want. Do you guys have any questions, or did you understand this demo walkthrough? I know it's kind of brief in my description in here, but.
So what are you going to do next with it?
Well, right now all I'm doing is I am getting an HDMI stream in and sending it to the processor, which isn't very useful. I actually want to do image processing manipulation in the programmable logic, and then potentially pipe it out the other HDMI. There's two HDMIs on this board. But you can also do a lot of image processing and then do the more advanced image processing on the processor. So you can do preliminary filtering and stuff like that in the programmable logic, and then send it up to the processor side, and then do the rest of the image processing there. And then you can send it out of Ethernet, or you could send it back out to the programmable logic. So it would be piped in through the programmable logic, do some intermediary filtering, go to the processor system to do more advanced image processing like object detection or something, and then filter that back out to the programmable logic to be piped through the HDMI output.
Why would you do more complicated stuff like object detection with the processor? Because otherwise you'd have to break all.
Because it might be very difficult to do in the VHDL. There might be IP cores for it, but I'm just trying to manage the complexity, and it's a trade-off of where you, like, I mean, obviously if I could, I'd try to do everything in the fabric. It's just way faster and more efficient, but I would imagine doing something like object detection is probably pretty complex in programmable logic, doing it in VHDL, because you have to imagine that this is digital design here, so you're basically manipulating circuits and gates, and like it's kind of difficult.
But if you were to do it, I mean, are there pros to it?
To doing it in the fabric? Yeah, similar to the pros that I mentioned before, which is just you get a massive increase in efficiency, and
In terms of
get massive parallelism.
okay.
You don't consume as much power, and you could potentially be better performance than you would be on a microcontroller. Even with a microcontroller with a very high-speed clock, if the application lends itself more to a parallel sort of application, then you might even get even more performance in the hardware, even though the hardware has a slower clock.
Like if you took a picture, instead of just like going like pixel by pixel, you could take all the pixels and do it all at the same time.
Yeah.
Like, would you, in best case scenario, would you always want to use an FPGA?
I
don't think.
No, and that's I was hoping. I was hoping that this wouldn't come off as me being like, this is the greatest thing ever, use it for everything. There's pros and cons that you have to consider, and it might not be the best thing for your application. It truly may not be. You could definitely explore this domain, for sure, I would, but you have to also consider, like, even if you did have someone who knew digital design backwards and forwards, it's a longer process than writing C applications. So it's like, what do you guys really need? I know that some of the stuff that you do, you could probably benefit from having battery powered stuff that be more efficient. It's very appealing, some of the arguments for this.
Signal quality stuff.
It's just like, are you guys in that point where, like, I know FPGAs offer like a flexible sort of design, but are you at the point where you've sort of at least locked down your design enough to know that an FPGA is the right choice to
I
use?
don't feel like we have any complex algorithms that need an FPGA.
Yeah.
So, well, okay. So, for example, right, for the things that I dream about, you got a bipedal platform, right? Could you, because like I'm still limited on knowledge about this. Like my understanding would be, so you have one FPGA, because my idea would you'd have a ladder system of cameras, not on just on the head unit, but rather throughout the main core, and you have all these cameras capturing image RGB values, right, and also maybe like syncing up that fabric, right, and then correlating it back to like what the head unit is seeing, and then almost at the same time creating like not just object detection, but also like creating like a three-dimensional world for the mobile suits, I guess, internal operating system to kind of be aware of, like I'm in this kind of space. So could you have an FPGA do, I guess, just take all of the camera inputs all at the same time, sync it up, process it, while having yet another FPGA manage all of the encoders for each motor joint, and maybe, I mean, that seems...
Yes, you can, because you're modifying hardware and you can do anything you want with it. It just matters how much space you have on the FPGA to do everything on a single chip. You might want to be concerned if you're doing a lot in FPGA. It's going to be less hot than a normal processor, but it still might require heatsink.
Because there's computer vision that's slamming, you're still going to need a lot of configuration. Maybe even a GPU.
You might be able to do like a bunch of systems all in one FPGA and then have like instantiate a soft core to sort of manage everything, because you can manage things easier in software land. So you can instantiate a soft core in the FPGA fabric and then do stuff there. But then if you really need like that many inputs, you might be better off doing just a pure standalone FPGA, because this is a SoC that has a hard core and an FPGA on it. But as a result, I have less fabric space. But for you guys, if you want like just a massive amount of IOs, like you can just get a pure FPGA that's just, some of these things are just stupid insane, where they have tons and tons and tons of, like over 1,000 like BGAs, like just IOs that you can mess around with, right?
Like the guy from Microsoft, he said he has like
That's another thing. If we're gonna be using like just the BGA, you need a multi-layer board.
Yeah.
So they have all the pins.
Yeah.
So it'd be even bigger.
But like
it's more expensive, the board itself.
Yeah.
Well, considering the scale of what I'm thinking of, that would be no problem.
Yeah.
My biggest concern for a mechanical would be heat dissipation and also like impact resistance, right?
Agree.
Okay. All right. I'm just going to open Vivado from scratch. You can get Vivado on the... It is free.
Oh, nice.
You just go to Xilinx, go to Vivado, and you'll get a link for it. Me too. All right. I'm going to open it. I already have Vivado open, so it's kind of nice. You can have multiple instances open at once. It's a big program, so it takes a little bit. I do, but I want to show you it from scratch. So here's the Zybo board. Here is in the shot. It's on right now. There's some switches on the board, right here. And then there's some LEDs right above those switches. All I'm going to show you right now is being able to flip on a LED, or sorry, a switch, and that turns on an LED. Right now you can see that if I turn these switches, nothing's on, so there's nothing preloaded onto the board or anything like that. So we're going to make a design right now. We're going to actually not use the block diagrams. We're going to program in pure VHDL. and I'll show you how to do that. So I'm going to go create a project. Step through the wizard, call it anything we want. LED driver. This is the name of the directory. Let's just call it FIBI. This is RTL is the type of design that you're doing. It's called register transfer level. That's just the name of this sort of design environment that we're going to be programming in. Yeah, you can look at it like that. Yeah. Right now, it wants to know if you have any sources that are from outside that you can import into here. I don't. I'll just make everything in here. So there's constraint files, and constraint files I can also add later, but I can show you adding it here now. Constraint files are basically how you've mapped the pins from the BGAs on the SoC out and where they physically connect on the board. And when you do that, you make a constraint file to tell it where things are, because FPGAs are so flexible, anything can be routed to anything else. So you make a constraint file to basically tell the software where things are. So you can refer to something like in software or in VHDL, you can say SW for switch, and then it will know what pin you're talking about. So it's just a map from where things physically are to what you're going to call it in your VHDL design. And when you buy like pre-made boards, like a lot of them, like this or any other board, they'll have a constraint file because they already have the SoC on the actual board. It's already been developed, and they already have the wires mapped to certain locations. Some are free GPIOs that are just going to headers like this. Some are dedicated to an LED. You don't want to get an ADC signal or any other type of signal for one that's connected to the LED. So you specify a constraint file saying, my signals on these pins are being routed here on the SoC. And you can get that on GitHub usually. A lot of vendors have that for a particular board. You just look up your board and then constraint file. I did that for mine. This is a Zybo Z7-20. And for me, I put it at the top location here, Zybo Z7 Master XDC. That's the extension name of the constraint files. And then also, a lot of the times, Vivado or Xilinx will have a lot of pre-made boards already. You need to tell Vivado what board you're working with. So you gave it a constraint file, and I need to tell, hey, like I'm using this board. There's a board file that you also need to give it if it doesn't default to it. Not for some reason, but like there's a lot of options here that you can choose for already pre-made boards. And if your board is there, you can just select it. If your board is not there, you need to do a little bit extra work. It's not that bad, but you just grab extra files from the vendor who gave you the board. They're called board files, and you can put them in a certain directory in your Vivado directories, and it will be able to say, oh, okay, cool, you're working with this board, and this is this particular part. And it just gives information about like what the pin count is. There's 400, and like other information that the project would otherwise need to be able to synthesize your design. So I'm working with that board. Finish. It's going to give you your dashboard. So this area is your project summary. So when you synthesize a circuit or when you're synthesizing your design, you can see right here, my synthesize has started, or how much memory you've consumed, or I mean, how many gates, how many resources you're consuming. There's also implementation. So generally how it works is you go through synthesis first, and then you go through implementation. It's just different steps that you need to go through to be able to generate a bit stream to eventually put onto your FPGA. So right now, what I'm going to do, here you can see the constraints. I can open up the constraints file and you can see what's inside of it. It's a bunch of commented out lines right now because I haven't specified that I'm using anything. Can you guys see that? Or is it?
So you just literally delete like the commented part out.
Exactly.
It activates.
Yeah, if I'm not using it, I'm not going to tell it to use it, right? But if I want to use, for example, a switch, these are SWs. You see is switch. So here's all my switches. It even has a comment at the top saying switches. And I have 4 switches here. There's 4 switches here. So that means if I use the nomenclature SW anywhere in my VHDL design, it's going to know, hey, you're actually referring to this signal coming out. This is what you must mean. And you can rename this to whatever name you actually want. So what I actually want to do is I want to uncomment all of these switches because I do want all of those switches. And then here's the LEDs that are right above the switches, and I want to uncomment all of those. They have the default name of SW and then array for the switches and then LED for the LEDs. I could change these names if I want to. I'll just stick with what they have. And I'll save this file. And now I'm going to add a source. I'm going to create the file myself. I'm going to call it LED driver. That's the name of this VHDL file that I'm creating. Finish, and then it actually, before it creates the file, it wants to prompt you of like what your inputs and outputs are going to be for this design. So you kind of design things in a modular fashion. So you can make a block for your HDL design and say, these are my inputs and these are my outputs. This is what's going out to the world. This is what I'm getting. And this is kind of how it wants you to set up the file. You can say, well, my port definitions here is SW. That's a switch. I'm using the same name as what's in the constraint file. This is going to be a bus because it has more than one. I have more than one switch, and that's how it was specified in the constraint file. So this is MSB, most significant bit, LSB, least significant bit. Just how many bits are you working with here to signify as switches? So the far right switch would be the least significant bit, and I flip that on, and then that would be a 1, 0. So here I'm just specifying how many switches I have. So it's 3 to 0 because I'm including 0. There's 4 switches. And then there's LED, and that's actually an output for me. That's also a bus, and that goes from 3 to 0. And that's it. I'm going to push OK. It's going to create a source with a template. All it did was just create a template for me. I actually need to define what the design is actually going to do. Here's the LED driver. So this is what it created for me. Not much. This is VHDL. It's specified in a .vhd file.
So that's like a sample module type thing? Or how does...
This is the name of, it's called an entity list. Those are your inputs and outputs going into and out of your design. Architecture is defining what it actually does. Before begin is where you have your declarations. You're defining variables here or declaring variables. Here below begin is where your actual design starts. And what I want to do is I want to have the switches drive the LEDs. So when I pull up on a switch, I want that switch to affect the LED. In fact, the same switch position, like switch 0, because there's 4 switches on here. Switch 0, I want it to affect LED 0. Switch 1, I want it to affect LED 1. Switch 2, 2, and so on. So to do something as simple as that, all you need to do, let's do that. And that's it.
Is it like a shorthand operator for something?
This is assigning switch to LED, and because they're the same width, 3 down to 0, 3 down to 0, I can do this. But if these were not the same bus width, I would have to typecast it. So this is a very, very simple design where you have the switches drive the LEDs. Once you've decided this is the design that you want, it's going to run synthesis and run implementation, and you can tell it to do those things specifically. But if you just say generate bitstream right here in the bottom left, it's going to run those 2 first anyways. It does that patch. So if you just want to do one step of the building process, you can. You might want to do that for analysis purposes. You don't want to take the time to build the whole entire thing. You just want to run synthesis because you can get information about your build once you do that. But if you just plan on doing the whole entire thing to get to the bitstream, then you can go one step after the other.
Is that like compiling and then running?
You can think of it like that. It's not. It's making a circuit. I believe that running synthesis is essentially taking your digital design and trying to optimize it.
Okay.
And then implementation is trying to run the routing and wires. Now keep in mind, when I do this, I'm not doing anything to the hardware right now. This is all in software. I don't even need to be connected to do this to the board. So all I did here was generate bitstream after I made my design. And yes, there are no implementation results available. Okay to launch synthesis and implementation. So it's going to run these manually. And again, I could run these manually myself if I wanted to. I just want to generate the bitstream. Here you can specify how many cores you want on your processor to actually do the work for you. This is an 8-core processor computer, so I want to use all 8 cores to be able to generate this. Push OK. And in the top right corner, you'll see the switch from ready to different states of the building process. You can go on the main dashboard here and actually see the progress of things. You always go to the main dashboard if you just want to see what state the project is in. Sometimes you close it and you go back into it. You can see where you left off. If you close this now, it would stop the synthesis and stuff like that. But you can see that this process is being queued, the implementation. So that will happen next after synthesis happens.
So now your computer and Vivado is interacting with the board right now?
No, it is not. I can unplug the board right now and things would still just be fine. All I'm doing is generating the bitstream to put onto the board. It's trying to create the digital circuit right now in memory and then trying to optimize it. So it creates it and it's like, okay, how can I make this better and more efficient? And the tool itself will actually try to optimize it in simulation itself. And then after it finds the best paths to route stuff, it's going to then try to write the physical connections.
So it's technically doing like millions of iterations right now to optimize?
I don't know the specifics, but I would imagine it would be something along those lines, yes.
So the implementation is when you have to report that?
The what?
When you have to actually
No, none. Like this step that I did, there's no process here that is flashing to the board yet. All I'm doing is generating a bitstream. I have to do another action here to flash the board. I need to go to Program and Debug and actually flash the bitstream that I've created. All I'm doing right now is generating the bitstream. So the synthesis just completed. Just to show you, I'll unplug this. So the board's not connected. Right. I'm still doing.
What are the 3 warnings about?
You never worry about your warnings. That means you did a good job.
Because it's not an error.
Yeah, there's different levels here. There's warnings, and then there's critical warnings, and then there's errors.
SolidWorks doesn't mean you be terrified of warning messages.
Oh, really?
Yeah, because if you ignore them, they will destroy your.
Yeah, some of the stuff you really need to pay attention to, and they won't stop you generating the bitstream, even though it will truly not work. So sometimes you need to be looking after that. But I know for something this simple, it's not. It's going to work. And this should show you, like, this is a really simple design. Like, I'm just connecting a couple wires, essentially. And it's taking this long. Could you imagine how long a project would take if I'm, like, building something significant like image processing? It takes a while.
Then you just leave it overnight.
Not that long. It might. So some of the builds that we do at work take, like, an hour or 2.
So what do you, on your laptop,
Yeah.
what are you using to make this? The processor or the GPU?
Processor. I have an 8-core processor. So when I kicked off the build, it asked how many cores do I want to use to do this work of creating the bitstream.
So, I mean, assuming you have a super crazy processor, like whatever, the max number of cores could just be faster.
Potentially, yes. For some parts, there's some parts that you need to do sequentially, like. I need to know the previous information before I go on with the next information. But there's a part here where I do synthesis where there's a lot of IP cores. I didn't even show you the IP editor where you drag and drop block designs in. We were just doing straight up VHDL. But for all these cores, they can be synthesized in parallel, and that's where you get to really exploit the cores in your computer to compile this.
Yeah, senior design, we were just messing around with the code. We weren't exactly sure if it was going to work. It takes so long, so we kind of just do 4 different things we thought. Let it go. We're like, all right, want to go bowling really quick?
Yeah. So what you want to do is you want to build a test bench and a simulation first with your VHDL design. I didn't do that because this was a very simple project, but you can build another VHDL file that runs an actual simulation, and you can see your signals. Remember in the video, I showed my, I call them integrated logic analyzers, and you saw the ILAs, they're ILAs for short, but you saw the signals being propagated through. That's what's happening in the programmable logic, and I happen to be running those in live time with the actual board, but you can actually simulate those, and you can say, if I give this my VHDL some stimulus, what is it going to do? And you can simulate what the signals are going to do based off of that. And that you can do that very quickly, and you don't need to wait this long for Bitstream to program hardware. When you have really big projects, you can't do that very well. You can't do it, like, it's almost impossible to do with some of the bigger projects. So I want to show you some cool, did it die?
No.
Oh, okay.
I was just.
I'm going to cancel out of this. I can go straight into Hardware Manager and flash the board. Notice, I'm not doing anything with the board right now, right? It's completely unplugged. It's not on. I'm going to cancel this because I want to show you. No, I don't want to take a survey. So there's simulation that it ran, right? I want to show you what a synthesized circuit looks like. It actually creates a circuit diagram for you of what you did in the hardware. So it's going to open that right now. That's super cool. Now with more complex ones, it's really hard to analyze these and look at them. But for something simplistic, you can actually look at the gates being used throughout the system and stuff. So we're popping that up now. There's another view that I'm going to show you that will show you the FPGA being lit up for different areas that you're using. This is it, but it's not. There's another. Let's see. There should be schematic. There you go. There's my switches, and then there's my LED, and then there's my switches driving my LED. It's a really simple design, but this is essentially what it did.
Would each switch be, or LED be like what you were doing before, where you could go inside of them and like really there's more going on inside of there? Like
Into these?
Yeah, those modules, are they more than just like a 1 or a 0, or is that what they are?
No, this is what they are. I don't think you can go any deeper than this into them. There's another area here where I want to open the implemented design. Yes, that's fine. This will take a second. But it kind of gives you the view that I did before, but it'll indicate different areas lit up on the board to show you where I'm using things. It's super small. There are areas lit up right here, 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 and here. So I think I don't have a, can I zoom in on this?
There's a magnifying glass info.
Oh, yes. There you go. If I zoom in super close, you can actually see the gates.
That's crazy. Yeah, that's awesome. Yes. Billions of little patterns just like.
So this is pretty cool. I don't have a mouse, so I can't really navigate this very well. But yeah, here's the FPGA. It's pretty cool. I wanted to show you the little areas that were highlighted if I could. So here's some of this that's highlighted over here. Yeah, I don't know how effective this is going to be. But you guys get the idea. This is, you kind of see where you're using stuff.
My brain's just one of those. I have like one left.
I for like half a core.
I just have gate up here. That's all I got. Forward. Not forward. If not food.
Do you see LED 2? That's the little area that's lit up.
Oh, nice.
LED 2. Yeah, yeah. It's this looks like a lot. There's FPGAs that are a lot bigger than this. Okay, so now that I showed you this, I want to actually program the board. So I'm going to go over to my program debug, go to Open Hardware Manager. So now, actually before I do that, there's in Project Manager, if you look at the dashboard, you can see that the synthesis and implementation are complete. And if you look at the top right corner, you see the right bit stream is complete. So I've made no changes. As soon as I start making changes to this, you'll see this saying out of date, which means you need to recompile it to match what your source is. But let's just go to the Hardware Manager. Let me connect my board. I can open the target. So now it's trying to connect to it.
It's like a local server assembly.
Yeah, I mean it's through USB. But
That's how the mechanism for running the flash.
yeah, they treat it like client-server relationship. Okay, there's a option here. I can either program the device right here in this option, or right-click this guy and do program device. So program the device right now. This is the bit stream that we just created. It's located here. It's called LED driver.bit. Now program it. When I do program it, whoops, I picked it up and it disconnected. Let's try that again. Didn't know the connection was that loose. All right, so when I flash this, there's a green light right here. You'll see that green light go off and then come back on once the bit stream's loaded. It's back on. So now, if I turn on the light, it's on.
Cool.
It's all happening in parallel. Yep.
Whereas before this would have taken much longer to do traditionally, right? Because you would have had to have like an Arduino connected to a bunch of lights and you got to code it.
Well, you could do exactly like what you did here with the microcontroller just fine. And you wouldn't notice any speed difference by the human eye, but this is truly happening in parallel, as with unlike a microcontroller, which happens line by line. It goes so fast that you wouldn't notice, but this is actually faster. Signals
So
operate
is there
faster.
anything that's truly parallel outside of hardware? Like even when they like use different cores and stuff like running together, there's still like synchronization and stuff that happens at like another layer, right? Like is that the same as
You mean synchronization with software and hardware?
or like so if something's parallel like at the hardware layer it's like literally because it's like physically connected, right? But like even two processors or something, like you know how in Python you have like two processes and then you like pipe and share
Yes.
data between each other.
Yes.
So like that would be like in my mind a step at which you're like kind of synchronizing like what's
Yes.
happening. But this is just like literally like electricity's never turning on.
Yes. But there are some designs where you need something to finish before something else, and you need to be in step with something.
Memory management when you have parallel stuff, because that was my first thought was like you might need to save something, right? And
Yeah. That's easier to support when you have like a soft core instantiated or a hard core. Sometimes you need to do handshakes.
Yeah.
So you can wait for a signal to go high on another chip or something like that. But that's essentially what it is. Yeah, it's just handshakes. So your like, I'm ready, and then this one can start that process, and that they have like two lines going to each other, one saying that this guy's ready and one saying that this guy's ready. And so you have to, it's equivalent to the software domain where you have to sometimes handshake between two different processes. It's just now you have to do it in the digital domain.
Yeah.
So that was, that's VHDL. That's how you do it pretty, a very, very simple switch. Now we can change this slightly and do other stuff. What I kind of wanted to show you guys was me creating a block diagram here. So if you wanted to create a block diagram, you can just go to create block diagram. You can name it whatever you want, push OK. It should happen any day now.
I haven't trust these things ever since you told me not to.
What, loading bars?
Yeah.
Yeah, they're a bunch of BS.
Like the one that the computer restarts and it's like 10 minutes and then it's like 40 minutes after it's 5 minutes.
Okay, so here's the pane where you do the block design.
I always thought, because like you can't know how long it's going to take sometimes when you're doing
Like when I'm
something,
just like
but they should
adding
just take the
like a
average
stupid
time, like for like
text file or
system
PDF
updates like
file to like
Windows, like
PDF.
record
It's all
what every
PDF file, but
user's
it's just like
average time is, and then you get a really solid average, and it just shows you
I'm
if you're at
so
50%
excited
because
and
you're at
frustrated.
60%.
So
Motor sticks.
if you want to download IP cores from different vendors, like there's people out there who have made cores that I don't have that I want. Some people put it out there for free. You can go to IP catalog and you can download their repo. So here's all the IPs, intellectual properties. That's what it is. Intellectual property cores. That's just what they call them. You can add a repository here. This is all the ones that Vivado has. I actually downloaded one from Git, and I put it.
What? IP on Git?
Yeah.
I thought those two things were not compatible.
Here I'm just putting the IP cores here. So now I have everything that Digilent, the people who made this board, they can give me their IP cores. So this is all their stuff. So now when I go back to the diagram, I can push the plus button and I can get all the IP cores here. So this is a bunch of like pre-made VHDL that you don't have to program. And there's like, for example, for the HDMI, the name of it is DVI. I don't know if you ever heard of that name before, but it's DVI to RGB. Oops. DVI to RGB, because I want to turn it into a form that I can actually manipulate the RGB stream if I have.
What is that difference between sync and source?
Sync is where you send signals to. Source is where you're getting signals from. So this is a sync. So you're getting. Yeah, this is so TMDS. I forgot what that stood for. Something differential signal. But this is, if you looked at HDMI, if you pulled up HDMI signals, like the actual signals that go into there's many signals that are routed through an HDMI cable. TMDS is some of the signals. If you expand that, here's the pins. You need to be very intimate with the actual signals that are going through cables if you want to connect it to your board, because it matters what all the signals and the lines are going to. You have direct control and you have direct manipulation over those lines that are going to your hardware. So this is TMDS. And there's also one for RGB to DVI. And here this core is. And if I wanted to, I can see RGB. You draw a line between them. And now I just drew a signal between those guys. And this guy has P data. There's 0 to 23, which is 24 bits, which is, RGB, 8 bits, 8 bits, 8 bits. It's 24 bits. So you're sending 24 bits to this guy. I know I'm not drawing the line specifically from here to here. You don't need to do that if you connect the entire bus. So automatically you have all these guys connecting to these guys.
So do these IP cores come like already associated with like a bit stream, or do you still need to make
This is essentially the source, and then you'll have to do exactly what we did with the other design, which is you have to generate a bit stream. You have clocks that are lined up together, A resets, they lined up together. You need some form of reference clock, which there's built-in stuff like a clock wizard. Clock, I think that's actually what it's called, clocking wizard.
casting time?
There's external hardware on the board that's an oscillator that actually feeds into the programmable logic.
So it's just the clock on the board in general. It's just giving you access to those readings.
Yeah, it's an interface to that. You can actually specify how far you want to divide it. So if you can double click on the IP cores and you have the ability to configure them. So this output clock, I want it to be 200 megahertz, and then push OK. So now this is generating 200 megahertz. If I wanted to go in here, I can actually manipulate this guy's IP and say, well, I actually want to do 1080p for videos that are going back and forth. Push OK for that. This guy, you can configure that one too. There's a lot of stuff that you can do in here and things that you can configure. You can make your own IP core, so what I just made with the VHD file, so this guy that we just did, you can make that into an IP core and drop it into your design. If you go to... Yeah, exactly. If you, I think, go to Tools and then create and package new IP, you can create the little block diagram and add it to your design here. But instead of going through all this stuff and actually making a design and synthesizing and everything, that's why I have another Vivado open, because I did all that. And that is right here. Yeah, I have a pre-baked pie for you. And I was going to flash it on here, but I don't think we have another... Well, actually, no, I think we could. Well, we need another HDMI cable. If we have another HDMI cable, I could actually show you this. But what this design is doing is it's feeding in the HDMI input from one side. And you'll see this here in a second. And it's being sent right out, back out to HDMI TX. So there's HDMI RX going in the DVI to RGB. It's feeding in here. No, not there. Here. And then going to HDMI TX. There's something called hot plug detection. So as soon as you plug in the HDMI into the RX, this will... I have this as a constant IP block. This just sends a constant signal of high out to this pin. So whatever connects to it, it'll tell that device that it's connected properly. And that's it. I mean, this is how I would sort of route the signals to... It's pretty useless design, but it's interesting in the sense that you're getting the video stream in, and you can manipulate it any way you want, and then you're sending it out. In fact, that's what I did on my previous design, or that's what I'm at least trying to work towards, is I'm trying to get stuff in, do image manipulation on it, and then send it out.
And with the clock, do you even have to know how that part works, or are you really just pointing it to where
Yes and no. You do in the sense where once I configured that, I'm feeding in sysclock. So sysclock has to be defined in the constraints file. All these ports here, they're external ports. They're named for a reason.
Exist in like real life.
They do.
Things that are on there, so
yes.
Outside of that, you don't, like, you're really just drawing
But,
lines to connect those.
But for yes. But to give it the proper names, this is the constraint file again. You need to tell it what period of the wave that you want. You need to be very specific. Yeah. Okay, we're pretty much done. I had to uncomment some of the HDMI RX to get that into the board, and the HDMI TX as well to get that into the board. So essentially what I'm showing here is just a combination of messing around with your constraints file to get output stuff onto the board into your design. and you can just add IP cores and generate a bit stream and flash onto the device and test stuff out.
I wonder it's so useful for just prototype.
Yeah. And actually, I might be able to do this since I've already built the bit stream. I'll go back over here and I'll try to flash this bit stream. There's a couple of built-in integrated logic analyzers. I don't know how much time I have. Is it?
It's just flashing red.
Oh, I see. All
That
right.
doesn't mean anything.
Okay, I'll program this device. So this is with this. So notice that there's two files here. There's an ITX and a bit file. The ITX is like a debug probe. So I put in my design integrated logic analyzer, or in reality, the vendors did. The DVI to RGB and RGB to DVI. Digilent made those IP cores, and they put in ILAs into the cores. So whenever I try to flash it, you'll see these window panes come up. And it gives you a glimpse into what the signals are doing inside of the core. So one of them I can't actually run because I need to have something connected to it. So when I try to run it, it's basically like, you can't do this, there's no clock on this line. But the other one, I can just run anytime I want. And it shows me what things are currently doing in the actual hardware. So this is live. This is actually what's happening right now.
It kicked me off the video.
Okay.
Does it change if you change values?
It will change if I plug in an HDMI to it.
Oh, got it. That one's not updated.
Yeah. If we can build in an ILA into our LED design, and you can actually see the signals go high and low. In fact, if you wanted to build in an ILA, let me go back to let me go back to the other design because it's a little bit lighter weight. If I do Control I can open up this ILA, Integrated Logic Analyzer. That'll pop out to the screen. So there's ILA. I can double click it because I want this to be not AXI, but a standard native probe. And I can put as many probes as I want. Like I want to analyze 10 signals. So I put 10 here. How wide bit width do you want the signals? You can have it all one bit long, or you can have it, our switch was 4 bits long because there's 4 switches. But I'll just keep them all 1 now just to show you an example. And then this is going to morph into having 10 probes with the clock signal. And now when I generate the bit stream, anything that's fed into there, like if I put this into one of the probes, or I put this pixel clock into one of the probes or anything like that, you'll see that on the...
So it just splits the signal kind of in the back. Is there a way to visualize it?
Yeah, exactly. Yeah, signals that are already used you can use again. You're just routing that, it's like a copper trace. Yeah. That's basically all I wanted to show you. I would have liked to show you this work in live time, but we don't really have the hardware set up to do that.
Next time.
Thank you.